Welcome to this video. I'm going to review the chapter number 5 of this special publication of economic geology. The title is Magmatism and Related Gold-Copper Mineralization in the Hualgayoc Mining District, Northern Peru. Here's a list of the techniques and methods used in this paper and innovative aspects of this study. First of all, they've used fusion method for preparing XRF samples, and it's the best way to ensure more accurate whole rock geochemistry by improving homogeneity across mineral phases. A key innovation when you're dealing with multi-phase porphyries and altered rocks. Then we have a combination of laser ablation and shrimp dating strategy for zircons. The authors used these two methods, which are complementary uranium lead techniques. This combination boosts accuracy and reliability of crystallization ages, especially when you have zoned or inherited zircons. Then we have integration of titanium in zircon thermometry. It offers a thermal history of magma evolution. It's quite crucial for understanding copper and gold mineralization potential, and to distinguish fertile versus barren intrusions. As I said, fusion method and sodium peroxide fusion has been applied for trace elements. It's a powerful method to digest refractory minerals like zircon or monazite that are typically underrepresented in trace element analysis. And finally, we have cross-checking magmatic fertility indicators with geochronology. By combining high-precision zircon dating with rare earths and trace element data, the study pinpoints when and how fertile melts contributed to an ore formation. Here we have a regional map. It's showing the Hualgayoc district of northern Peru. It's a region where complex magmatic evolution and structural controls have produced a unique overlap of porphyry, copper, gold, and molybdenum with high sulfidation epithermal and the skarn systems altogether. This area is centered around the Cajamarca region, which lies along the Chiquicama-Yanacocha structural corridor. Between approximately 14.8 to 9.7 million years ago, repeated pulses of Miocene magmatism intruded the upper crust in this region. Some of these magmas were fertile and ore forming, while others remained barren. High precision zircon geochronology and trace element chemistry provided critical insights to understand the geology of this area. Zircon crystals, which are resistant to alteration, are capable of recording magmatic conditions. They can reveal ore-associated intrusions were more oxidized, water-rich, and in place at vertically oriented stocks. These conditions favored sulfide saturation, fluid exsolution, and finally ore precipitation. Here key systems in this district illustrate different evolutionary pathways. We have Cerro Corona, which represents a classic porphyry system and is characterized by long-lived magmatic activity, moderate oxidation states, and fluid evolution conducive to copper and gold deposition. Then we have Tantahuatay. It's a hybrid system that records porphyry-style mineralization overprinted by later high sulfidation fluids with evidence of scar and development at depths. The distinguishing factor in this metallogenic cluster is not simply the magma chemistry, but the architecture of its emplacement. Vertically extensive and long-lived magmatic systems provided the thermal and structural framework which are necessary for fluid retention and ore-forming reactions. In contrast to the systems with low intrusion rates, subhorizontal geometries, or limited volatile content, they fail to produce significant mineralization despite having similar geochemical signatures. So to summarize this slide, the Hualgayoc district highlights that the formation of large-scale copper-gold deposits depends not only on having fertile magmas but also on sustained structurally focused emplacement, elevated oxidation states, and favorable hydrothermal dynamics. These insights reinforce the importance of integrating geochronology, zircon chemistry, and structural geology in porphyry exploration. Here we have a summary of tonnage and grade data of deposits for Cajamarca district. First up we have Cerro Corona. It's a textbook porphyry gold and copper system. It's hosted in dioritic intrusions and dated to around 14.5 million years ago. It holds more than 110 million tons of ore, with grades of 0.5% copper and 0.9 gram per ton gold. It delivered 54 tons of gold and over 70,000 tons of copper. It's quietly becoming one of the region's most efficient producers. Then the next deposit is Tantahuatay, just to the north. This deposit lies as a high sulfidation gold-silver system. Unlike its porphyry neighbors, this one is acidic, volatile rich, and hosted in andesitic volcanic rocks. With 220 million tons of ore and a gold grade of 0.33 gram per ton, it's optimized for shallow processing and rapid extraction. Then we have Hattori. It's a geologic hybrid, scar and porphyry in an epithermal system. They all collide here in a limestone host rock. This deposit contains more than 517 million tons, including 2.3 million tons of copper and 140 tons of gold content, as reported in 2019. So it's a true polymetallic frontier with depth, complexity, and promise. Zooming out to greater Cajamarca region, you can see that the scale of mineralization becomes even more impressive. We have Minas Conga, and we see that it contains 641 million tons, grading 0.28% copper and 0.75 grams per ton gold. Not far off we have El Galino, which adds 486 million tons at 0.57 copper, supported by molybdenum values. And then there is Michiquili or Michiquili. It's a copper powerhouse with 630 million tons and the highest copper grade in the region at 0.69%. This system is both rich and robust, with up to 200 ppm molybdenum values. But when it comes to gold, in this area, nothing compares to Yanacocha. Between 1993 and 2010, this deposit produced over 1,225 tons of gold. And even by 2019, it still held reserves of 216 tons of gold and 0.66 million tons of copper in its deeper sulfide zones. So what we can learn from this regional snapshot, these deposits span styles from porphyry, skarn, high sulfidation, and ages from 20 to 8 million years. But many share a host rock, which is dioritic intrusions. Age, chemistry, and plumbing all come together to define these giant deposits. So for explorers and junior companies, this is not just a table, it's a roadmap. If you follow the patterns in style, age, and rock type, you're not just studying history, you're anticipating the future of discovery. In this map, we are now zooming more into the heart of northern Peru, the Hualgayoc district. It's a mineralized corridor where Miocene intrusions meet Cretaceous sediments, and complex structures focus hydrothermal fluids into world-class deposits. So geology here is a mosaic of Miocene volcanic intrusives and Cretaceous limestone and sandstones. Intrusive units are shown in red, pink, and purple, and Cretaceous sandstones are green and yellow. This contrast, we can see a contrast between host rock and host rock types. It plays a critical role in ore formation, especially for skarns like Hattori and high sulfidation systems like Tantahuatay. We have 4 key deposits anchor this region. As I mentioned above, Cerro Corona. It's a porphyritic coarse diorite intrusion placed into limestone, and it formed a gold-rich porphyry system. Tantahuatay is an andesite rhyolite dome complex with shallow intrusions and intense acid sulfate alteration. It's a classic high sulfidation deposit. And Antacori, which is a polymetallic skarn system overprinted by porphyry and epithermal fluids, and exploiting limestone contacts and structural corridors. And finally, Cerro Negro, which is located on the western margin. This rhyodacite dome is part of a broader Miocene magmatic belt. Here, structural geology is crucial. You can see multiple northwest trending faults cut across the region, acting as pathways for magmatic and hydrothermal fluids. Fold axis and bedding attitudes suggest early compression, while later extension opened space for intrusive domes and breccias. Overlying this framework are hydrothermal alteration zones. We have silver-rich veins aligned with faults. We have pyrite energite bodies mark zones of intense acid leaching, and widespread breccias signal explosive volatile activity, especially near Cerro Izes and San Jose. These markers define the thermal and chemical architecture of the system. So, to summarize this slide, in this district of Hualgayoc, we have voluminous Miocene intrusions, we have carbonate host rocks, multiple fluid pulses, and complex fault geometries. Together, these all created a multi-style, multi-stage metallogenic system, which is ideal for gold, copper, silver, and molybdenum exploration. And for exploration companies, this map is a structural and temporal blueprint for targeting Peru's next copper and gold discoveries. Here we have a minor scale local map. We have Cerro Corona intrusive complex. It's a compact multi-phase porphyry system within Cretaceous limestone host rocks. It records a precise sequence of intrusive events that collectively define its mineralizing architecture. In this map, each color represents a distinct magmatic phase or pulse placed over a narrow but critical window between approximately 14.6 and 14.4 million years ago. And those ages are confirmed by uranium lead zircon geochronology. We have phase 1 and phase 2. They dominate the outer zones, likely representing LD and less fertile pulses. We have phase 3 to 5, transition inward, building complexity. And we have phase 6 in blue, which is the latest and most focused and likely tied to vertical fluid migration, which enhanced copper-gold mineralization. This structure here is not random, it's vertically zoned, with upward flaring stalks that tap deeper sources and inject fluids into fracture networks. This geometry is key. In porphyry systems, it's not just a magma chemistry, it's how and where the magma intrudes that control its metal distribution. The surrounding Cretaceous limestone here is shown in green. It's passive, it reacts intensely with hydrothermal fluids, promoting scar alteration and enhancing metal precipitation. These 6 phases here, they all share broadly similar mineralogy. But only specific ones are spatially and temporally linked to potassic alteration and copper-gold winglets. This highlights a key porphyry principle. If you have multiple pulses and intrusions in a region, they're not all mineralized. You need the right timing, geometry, and pressure temperature conditions to create a porphyry system or mineralization. Cerro Corona intrusive complex is more than a map. It's a kind of time sequenced 3D puzzle of magmatic evolution. And understanding these internal zonations and their structural context helps us unlock where, when, and why mineralization occurs. Okay, we have surface geology of Tantahuatay San Miguel district here and cross section. The map outlines a complex volcanic and intrusive terrain, primarily within Miocene-aged Calipi volcanic sequence. The red dashed boundary defines the surface extent of high sulfidation and skarn-style mineralization. You can notice the purple breccia bodies. These are mild heterolytic breccias, typically associated with zones of fluid overpressure. Multiple subvolcanic intrusions, including felsic domes, San Miguel diorite, and Calipi subvolcanic stocks. They are distributed along structural corridors, which indicate a magmatic plumbing system fed by deeply rooted faults. We have the cross-section view on the right panel, slicing southwest to northeast across the district. Here we see a stacked magmatic hydrothermal system. Brown intrusions represent porphyry stocks. Pink ones are heterolytic breccias seen at surface, now shown cutting through multiple lithologies. We have orange and yellow domes represent felsic intrusions and younger Calipi volcanics. And the red dashed outline shows the vertical extent of mineralization, extending to almost 3,000 meter elevation, which is controlled by both lithology and fault orientation. At depths, Calipi subvolcanics intrude folded sedimentary sequences, and beneath that lies the Cholic and Inca formations. There are limestones that have undergone extensive skarn mineralization, and they formed an ideal host for copper-gold mineralization. So this is not a single episode system, it's a hybrid that integrates elements of porphyry, copper-gold, high sulfidation epithermal activity, and skarn-related mineralization. The geological architecture here reflects multiple intrusions with explosive brecciation and prolonged fluid rock interaction driven by a complex interplay of magma pulses and structural reactivation. So, what's the takeaway here? The Tantahuatay San Miguel system exemplifies how vertical magmatic plumbing, structural permeability, and reactive carbonate host rocks can combine to generate a multi-stage, multi-style mineral system, which is highly prospective for copper and gold exploration across the whole Andean belt. Here we have geochemical results. Let's start with panel A. These are REE patterns for weakly to moderately altered samples across the Hualgayoc district. You can notice the shape, it's moderately concave up, especially enriched in LRE like lanthanum, cerium, and neodymium. This enrichment is consistent with oxidized hydrous magmas, and which are commonly associated with fertile porphyry style systems. The middle two heavy REs from europium to ytterbium, they plot relatively flat. This suggests minimal fractionation or stabilization of those elements in resistant phases like zircon, titanite, or amphibole. In panel B, we have intensely altered sample results, and it tells a very different story. We see strong depletion in middle and HREs. It's a steep decline from samarium through ytterbium. This is typical of hydrothermal leaching, particularly under acidic oxidizing conditions such as those in advanced argillic or skarn style system zones. The gray shaded field outlines the typical range for least altered rocks in the region, and it's a kind of geochemical baseline. We have samples like Tanta 352 and Tanta 357 and Anta 6 plot far below this range, which are clear evidence of extreme fluid overprint. An interesting outlier here is sample 25-4 from San Jose. It's been strongly weathered, but it retains some LREs. Possibly it's because surface weathering is less effective at mobilizing these elements compared to deep hydrothermal fluids. So why is this important, these geochemical results? Because RE patterns don't just reflect magmatic input, they can map the intensity and type of hydrothermal overprints too. Low MRE and HRE values signal fluid pathways, alteration intensity, and potential metal transport zones. So if your rocks are missing rare earth elements like terbium or dysprosium, you might be sitting on top of a hydrothermal engine that already moved copper and gold. It could be the most important takeaway of this slide. Here we have timing and magmatic pulse chart. We have zircon results for different deposits. This image brings together two layers of insight. On the left, it's a geologic map showing spatial patterns of intrusive units, and on the right is a precise geochronological chart based on uranium late dating of zircon. We have green groups with 14.8 to 14 million years. These are the earliest pulses of magmatism in the Hualgayoc district. Key players here are Cerro Corona, San Miguel, San Jose. They're all likely linked to early porphyry formation and initial hydrothermal circulation. These are the intrusions you want to study if you're hunting for the core mineralizing events in this district. Then we have red groups with intrusive activities from 13.7 to 11.5 million years. This group includes the Tantahuatay intrusions, A through D, Calipi, subvolcanic rocks, and some other intrusions. What's striking here is how widespread this pulse is. It cuts across much of the district, and it suggests a regional magmatic reorganization, possibly triggered by slab shallowing or maybe a renewed arc magmatism. These intrusions may overprint earlier mineralized systems or intrude epithermal and skarn overprint on porphyry frameworks. And finally, we have the blue dot groups. They are a lonely rhyodacite intrusion dated at 9.7 million years, and it's far younger than the rest and may represent the final gasp of magmatism in this district. Located in the northeast, this unit is likely post-mineral, but it provides a cut-off age for hydrothermal activity in this region. Now let's zoom into the map. The green intrusions cluster in the northwest and central corridor. The red intrusions arc through the southern and eastern areas, and the blue rhyodacite sits alone to the east. This spatial and temporal separation helps unravel the tectonomagmatic evolution of this district. For exploration companies, for explorers, this is not just stating results. These age constraints help prioritize drill targets. For example, if copper gold mineralization is associated with green phase porphyries, then intersecting younger red or blue units might indicate overprinting or barren late stage intrusions. Also, correlating zircon ages with alteration style helps refine exploration vectors from early potassic cores to later propylitic or advanced argillic halos. Here we have the results of amphibole chemistry, and we have classic pressure temperature diagrams based on the chemistry of amphibole. We have red zones, and they mark serocorona amphiboles formed during ore deposition. There are your mineralizing intrusions in this area. We have blue zones. These amphiboles formed after the main mineralization phase. They are hotter but show no economic mineralization, and they miss the main metal delivery window in this area. Then we have green triangles from Koi Molache. It's a neighboring deposit with similar depths and temperature, possibly linked in time or style. And finally, we have red. We have diamonds from San Nicolas, which is the same region, but much lower pressure, and it's likely shallower crystallization or altered tectonic setting. In terms of P&T conditions, most mineralizing amphiboles cluster between 850 degrees and 200 megapascal, which is about 5 to 7 kilometer depths. And then we have a gray line. This is the thermal stability curve for amphibole. Mineralizing samples formed at the limit of amphibole crystallization. This is the sweet spot for porphyry systems, hot enough for fluids and stable enough for amphibole growth. In panel B, we have redox versus temperature. This controls metal solubility, sulfide stability, and finally ore deposition. Here again we have red and blue fields. They are seen and post-mineralization amphiboles from Cerro Corona form distinct clusters in this diagram. The red group plots around FMQ +1 to +2, which means oxidizing magma, and they're ideal for copper and gold transport. We have FMQ lines here, which are the buffer curves, and they are standard in industry for redox calibration. In this diagram, red diamonds of San Nicolas, they show low fugacity of oxygen, well below FMOQ, which suggests a reducing barren system. And we have a red line, which is SO2 H2S buffer zone. This tracks the presence of sulfur gases, essential in forming sulfide ore. The overlap tells us that SO2-rich fluids were likely involved in mineralization in this area. And finally we have panel C, which shows aluminum content versus temperature. It's a proxy for pressure and melt composition. We have seen mineralization samples here in red. They cluster around 825 to 875 centigrade degrees with moderate aluminum content. They're ideal for ore-forming magmas with high water content. We have blue zone, which is post-mineralization, stretching to the 900 to 950 centigrade degrees. They're hotter, but with similar aluminum content. They may be trapped deeper and as drier magmas. And we have a dashed line here, which is pre-Miocene. They have it's a zone of chemical different chemistry altogether. These amphiboles formed before mineralization, and they're evolved with low aluminum and low titanium. Low temperature. So what's the takeaway here? High temperatures are not enough. You need the right chemistry and pressure to generate ore-forming fluids. And only specific magmatic pulses hit this mark. The takeaway here is that amphiboles record the conditions of magma crystallization, including pressure, temperature, oxygen, and water content. And if we can decode these signals, we can predict where the ore is and where to avoid wasting drill meters. Amphiboles are not just minerals, they're thermochemical GPS units buried in the rock record. Here we have amphibole results tracking magmatic fertility. And zircon-derived fugacity of oxygens. Let's start with the circles and stars. We have green circles. There are zircon-derived fugacity of oxygen using the LOX 2020 method, and we have stars, which are Smythe and Brennan 2016 method. We have same parameters, different modeling approaches. The authors here applied 2 different approaches, and was quite smart. We have y-axis, which is a log of oxygen fugacity, and each point on the y-axis shows how much oxygen was in play. Higher oxygen, more oxidized, and that's the key for carrying and depositing metals like copper and gold. In x-axis we have temperature, which ranges from 600 to 900 centigrade degrees, and those are magmatic temperatures, which are a sweet spot for zircon and amphibole formation. Then we have FMQ buffer lines, which are oxygen buffer curves. FMQ +1, +2, and +3. By the way, FMQ stands for Fialite, Magnetite, and Quartz buffer. It's a geochemical reference, and the way to standardize redox measurements across different systems. So when we say FMQ +1, +2, it means that the magma was 2 log units more oxidized than a neutral buffer. Most fertile porphyry magmas fall between FMQ +1 and +3, and that's exactly where many of these points land in this diagram. Now we add in another data set. We have amphibole derived redox 2. We have green triangles, which are amphiboles from Koimulake. We have diamonds from San Nicolas, and these are direct mineral proxies formed in hydrous magmas, often before or during ore formation. And what do we see here? The amphiboles and zircons, you can see they converge, overlapping in the FMQ +1 to +3 range. And that convergence is powerful. It means 2 independent minerals agree that the magmas were highly oxidized. And then SO2H2S buffer line of red curve. It marks the boundary where sulfur transitions from being dominantly in sulfide form to sulfur dioxide gas. Why does it matter? Because sulfur in gas form is essential for transporting metals like copper and gold and molybdenum. So if your data, it means that if your data plots above this red line, that's a major green flag for porphyry style mineralization potential. So this diagram is not just academic, it's a kind of exploration tool. If your zircons or amphiboles plot in the FMQ +2 or +3 zone at moderate to high temperatures, you're likely looking at magma that had the right ingredients to form an ore deposit. But if you're down at FMQ or below, that's a red flag. It's likely a barren or sulfur deficient magma. So what's the takeaway? By combining zircon and amphibole geochemistry, we can map the redox evolution of magmatic systems and identify which pulses were capable of forming all porphyry, copper and gold deposits. High fugacity of oxygen, high sulfur activity, and moderate to high temperatures. That's the winning recipe for porphyry systems. So all of that is locked in the chemistry of these tiny minerals. You just need to know how to read them. Here's the final slide and then conclusion takeaways here. First of all, we have oxidized water-rich magmas in fertile systems. Both amphibole and zircon data revealed that magmas responsible for mineralization were highly oxidized, above FMQ +1 to +3, and contained over 3 weight% water. These are textbook traits of fertile porphyry systems. High oxygen fugacity increases metal solubility, while water content drives magmatic overpressure and fluid release. The second thing is 3 magmatic pulses. Timing is key here. Zircon uranium lead geochronology identifies 3 distinct magmatic pulses or episodes here, and the majority of mineralization is linked to the first 2 pulses. So age dating is not just academic, it's a real targeting tool for exploration. Then we have thermobarometry pinpoints depths and temperature. Amphibole barometry shows mineralizing intrusions crystallize at pressures of 150 to 200 megapascal, and that's about 5 to 8 kilometers depth, and temperatures near 850 centigrade degrees. And that's the sweet spot for porphyry formation, deep enough to accumulate metals, but shallow enough to exsolve ore-forming fluids. The next thing is amphibole and zircon as geochemical compass. These minerals are more than just tiny crystals. They're trace element signatures, especially cerium and europium anomalies, and redox sensitive REs act as vectors. They help us distinguish between barren intrusions and those charged with mineralizing fluids. And finally, we have integrated multi-technique approach, which is quite critical. We can see that no single data set tells the whole story. It's a combination of uranium lead dating, titanium in zircon thermometry, amphibole redox estimates, and rare earth element chemistry that builds a complete picture. and together these tools chart the full magmatic and metallogenic evolution. Thanks for watching.